We have now so far discussed how to write representations of SUSY algebra on one particle state. Today we'll start discussion of how to write SUSY representation on fields. Representations of SUSY algebra on fields. We shall restrict to n equal to 1. So only one set of SUSY supersymmetric generators. So on a generic field, let's call it capital phi x. It could be a scalar, fermion field, or a vector field. How would the SUSY act? It would change phi by an amount, we call it delta phi, and that would be I times the commutator of let me introduce an object called epsilon. Alpha is a spinor object times q alpha. Q alpha is a supersymmetric generator, and q bar alpha dot is conjugate times epsilon bar that's how. Is there a minus there? No. Okay. We have introduced epsilons here. Epsilons are the amount of transformation, parameters of transformation. So epsilon alpha and epsilon, yes, alpha and epsilon bar alpha are parameters of transmissions. Since these are anti-commuting objects, they are anti-commuting objects. Anti-commuting. What does that mean? These anti-commute with any fermionic object and commute with a bosonic. Since we have given an index alpha on a spinor index alpha, they also transform under Lorentz transformation. Epsilon alpha transforms as half zero representation, epsilon bar as zero half representation. And what do we mean by anti-commute? They anti-commute amongst themselves. And also, if I have a fermions in my theory, or for example, with Qs, because Qs are also fermionic, so they anti-commute, and so on with Q bar also. So similarly, but with bosonic objects, they commute. Let me take P mu. This is the standard way we write a change of a field under a symmetry operation. The generator of the symmetry operation, commutator of that with the field operator. This is the infinitesimal version of the fact that under a symmetry transformation, if a field phi changes to phi prime x, that is given by u x u inverse, where u is exponential I times epsilon alpha q bar dot alpha epsilon. That's the full change. And if I write an infinitesimal change, expand this as 1, I'll write a shorthand for, this can also be written, a shorthand is epsilon q plus q bar epsilon. By this we mean epsilon alpha up, q down. The sequence on undotted ones, in order to write this notation, is first one up, second one down. And for barred ones, which are dotted indices, q alpha bar alpha dot down and epsilon up. So that is the convention. So u is epsilon q plus q bar epsilon times an I. And this is what we call delta phi. Change in phi is that's what we wrote here.
Q's and P's are your operator for the constant.
Yes.
Whereas epsilon is
Just a parameter.
So what does it mean by this?
Commutator means simply this times this plus that time this, which means I can take this across with a change of sign.
But epsilon doesn't contain any A's and A, right?
No, epsilon is just a parameter. Yes, right. Well, you use the word. Yes, it's just a parameter. Because these are fermionic transformations, we need a fermionic parameter. In gauge symmetries, you put, for example, xi or theta as a parameter of transformation. The amount of transformation images how much of transformation you are doing it.
So that means Q also contains some Grassmannian variables that we
Q is fermionic.
What I mean, apart from the A and A dagger satisfying the fermionic combination, you also have some Grassmannian variable also.
It is more than Grassmann variable. This is number. This is an operator.
Yeah.
It is more than see. This is generalization of a number. Whereas this is an operator.
Yes.
Okay.
The operator part is A dagger.
A dagger. Well, A is also we put them as fermionic oscillators. A daggers, right? Yes.
But
so they are also anti-commuting.
But they commute with epsilon because epsilon is a
anti-commute.
Why is it anti-commute?
Because they are fermionic in nature. That's the definition of epsilon. That is the rule we are giving epsilons. Epsilons are defined by these rules, these properties.
So I mean, epsilon with A, just A or A dagger, will it anti-commute?
Now, depending upon A and A dagger, whether it is a bosonic oscillator or fermionic oscillator.
So if it is a fermionic oscillator,
yeah, anti-commute. So this is what we have. Now, we'll discuss this in a little more detail maybe later. What do these parameters mean? For us, these are some symbols with these properties at this stage. Now, what did we have? We had SUSY algebra, Q alpha, anti-commutator with Q bar alpha dot was 2 sigma mu alpha alpha dot p mu. That is n equal to 1 SUSY algebra. Now, this SUSY algebra, if I just multiply by epsilon alpha from this side and epsilon bar alpha dot from this side up. So this object will become epsilon alpha, Q alpha, and this will become Q bar alpha dot, epsilon dot. But multiplying these epsilons will do something. It will change anticommutator into commutator. Because of these rules. You write this as two terms, the first term plus second term, and multiply epsilons. You'll see that you'll take an epsilon across in order to make this combination again once or odd number of times. So that will change the sign of the second term. Unitary, yes, it is. So since he has asked the question, because dagger operation interchanges there. All right. So this has converted this converts anti-commutator to a commutator. Fair enough, because epsilon times Q is a Lorentz scalar. It's a fermion, it's a fermion, this is a bosonic object. For bosonic objects, we must prescribe commutators. Now, how does this algebra how is it realized on fields? SUSY algebra is realized on fields as the commutator of two transformations acting on the fields. That is, I make a transformation delta epsilon 1. So let me call this delta epsilon, transformation by an amount epsilon, the commutator of two transformations acting on fields. So let me evaluate this on the field, given how it single transformation X on the fields. So I'll just use a symbol delta 1 for this and delta 2 for this. Delta 1 is transformation with parameter epsilon 1, delta 2 is transformation with parameter epsilon 2. So what do? I make two transformations. First, delta 2 on phi of X, then make a transformation delta 1. So let me make two transformations in succession, delta 1 and delta 2 on phi. So delta 2 and delta 1 on phi of X. Delta 2 on phi of X is I times Q epsilon 2 plus Q epsilon 2 Q bar epsilon 2 bar commutated with phi X. And this is now another I, so minus delta 1 epsilon 1 Q bar epsilon 1 commutator with this object, commutator Q bar epsilon bar phi X. This commutator and this commutator. So delta 2 on this is commutator of E2Q plus Q bar epsilon 2 of phi commutator. Then make this second one delta 1, that gives me another I, so that's minus. So this object commutator of this commutator. And let me do this now in other sequence. Is it clear? This is double commutator. Commutator of this with this, and then commutator of this with the result of this. And let me subtract them out. That's what I mean here. This is what I want to evaluate. Now do this algebra exercise and convince yourself that this is commutator of epsilon 1 Q plus Q bar epsilon 1 bar commutator epsilon 2 Q plus Q bar epsilon 2 bar with phi of X. Write these in longhand. Various some terms will cancel out and you will be left with this. Commutator of epsilon Q plus Q bar epsilon bar with this one and commutator. I think there's a minus sign there. Yes. Huh? Can you do that? Now this object, we know what it is from the algebra here, except that we put the same epsilon here, but there is 1 and 2 or 2 and 1. So therefore, this is epsilon 1 q, this with this, q bar epsilon 2 with phi of x. That is one term. The other term is this with this, but they have a different order. Than q bar is first, then q. I change the order and change the sign. This one is with this and this, sorry, this and this. Commutator of this one and this one is 0. That's a 0, SUSY algebra. Commutator of this and this is 0. Now I can read this off from the algebra here. Minus 2 epsilon 1 sigma mu epsilon 2 bar, and this is minus epsilon 2 sigma mu epsilon 1 bar. Now what's P mu on phi? Translation operator. X is a derivative. Notice P mu on x nu acts as minus I d mu on x nu. So P, and which is minus I d mu x nu. The translation operator P mu, momentum, on x nu acts in this way, but on fields it acts with important sign. And that's very simple to see, is that this is some we have done it again and again. A field phi transforms so if I have a frame, say x1, x2 here, and if I translate this frame to, let me say, x1 prime, x2 prime by an amount xi prime, so that x mu prime is x mu plus xi mu. Then given a point here and a field defined on at that point phi x, in the changed coordinate is the same because it's the same field, but it's a prime in phi prime in x coordinates, in x prime coordinates. Clear? This is field sum, whatever value it is. If I measure it in x coordinate, it's phi of x. If I measure it in prime coordinates, it's the same object, so give that name a phi prime of x prime. Now phi prime of x prime is that, what is phi prime at x value? Because x prime is this. this is phi of x minus xi mu d mu phi. Make a Taylor expansion. And this, in terms of translation generators, would be I times pu mu of phi. P mu as an operator. So that tells me P mu of phi has to be this in order to get that, times xi mu. Is that clear? So now use this and we write supersymmetry algebra, how it would be realized on phi's. It would be realized by transmission by an amount epsilon commutated with transmission by an amount by parameter epsilon 2 is minus 2 epsilon 1 sigma mu epsilon 2 bar minus epsilon 2 sigma mu epsilon 1 bar times an I. This is how it would act on a generic field phi x. Now this is again shorthand notation of epsilon 1 alpha sigma mu alpha down alpha dot. So in the shorthand notation, whenever we contract up and down for undotted ones, down and up for dotted ones. So this is our master equation. So all now we have to do is that find out representations of fields that satisfy this master equation. So we start with a representation what is called chiral multiplicator. So start with a complex scalar field. Small phi of x. Now, P mu has mass dimension 1 in unit c equal to 1, h cross equal to 1. P mu is energy or momentum is all like mass in the units, mass units. And Q is in some sense square root of P. So mass dimension of Q is half. Both Q and Q bar. Can anybody tell me what should be the mass dimension of these transformation parameters? Second chance. Second chance. Huh? Minus half. This object has to be dimensionless. It's an exponential of something, exponential I. So if Q is half, epsilon is minus half. So anyway, that's an SI. Mass dimension of epsilon bar is minus half. So if Q is dimension half, if it acts on a scalar field is dimension 1, it must increase its dimension by half unit. So therefore, Q SUSY acting on a field of dimension n, mass dimension n, this is mass dimension, should change it into a field of mass dimension n plus half. It could also change into or a derivative of a field of dimension n minus half, because derivative has a mass dimension plus 1. Is that clear? So phi, which is mass dimension 1, under this transformation should get into transform into mass dimension 3 half object, and mass dimension 3 half object is a fermion. So delta phi has to be proportional to a fermion. Call it psi. And this, but this has to be a Lorentz scalar, because phi is Lorentz scalar. So psi alpha, epsilon alpha, the transformation parameter, amount of transformation. Is that clear? Just by on dimensional grounds, if phi has to transform, it will have transformed to a fermion, and amount of transformation parameter is epsilon here. With that, you make it into a Lorentz scalar. Clear? And you sneak in root 2 just for convenience. Now scalar field is mass dimension 1, and change in scalar field also has to be mass dimension 1. So this together has to be mass dimension 1. This is 3 half, this is minus half. There's another way of saying why it should be minus half. So that this is together mass dimension 1. Now, you said I put a psi there, psi alpha, but so psi alpha is a fermion in representation half 0 of the Lorentz algebra, and mass dimension 3 alpha. I could have also put a fermion here in the 0 half representation. This is a left-handed fermion. I could also have put a right-handed fermion, but I have not done that. So what we are talking about is we are talking about a supersymmetric transformation where phi gets transformed by by q alphas, but does not get transformed by q bars. Otherwise, we should have put a corresponding 0-half representation also, which means we are trying to construct a multiplet where the scalar field, complex scalar field, transforms only on unbarred supersymmetric generators, but not under barred supersymmetric generators. Another way of saying that is that epsilon bar q bar commutator with phi of x is 0. So this is a choice or a constraint. So we impose this constraint on the representation. What does this tell me? It tells me is that phi transforms only under the left chiral supercharges, but does not transform under the right chiral charge. Now you understand the word chiral representation. We call it chiral multiplet. So this is the reason why we call this a chiral representation. Is because this representation has the property that it does not transform under the q bars, the right-handed supersymmetric charges. It transforms only under the left-handed supersymmetric charges. Okay. Given that, now I must now give you what is the change. This is phi of x. How does psi transform under supersymmetric transformations? So delta epsilon on psi alpha. Psi is mass dimension 3/2. So it must change into a field of mass dimension 3/2 plus half is 2. And 2 derivative of phi is dimension 2. But now this is fermionic. This must be fermionic. Mu has been contracted, so there is no mu, and sigma mu alpha, this is the shorthand for sigma mu epsilon alpha, is the shorthand for sigma mu. Mu's have indices alpha dot, epsilon bar alpha dot. Alpha is the free index. Alpha dots are summed. So this is what it can be. And you put in a factor of 2 and an I here. Is that clear? Just on dimensional grounds, this is the choice I have. And these factors are just put in by convenience. That I'll tell you how to fix this. But before that, this has to transform to a field of dimension mass 2. This is one we constructed. There could be another dimension 2 field in my theory in this representation. So give it a name and call it F. Three half plus half. Fermion is 3/2. Q will change its dimension by plus half. add. So that is 2. So this is 2. So I add a field of dimension 2 to this multiplet, and to take care of the spinel indices, multiply by epsilon. And again a root 2 for convenience. Just by dimensional grounds, nothing more. Because you wanted this Lorentz, you want it to half zero representation.
We are looking at variation of phi, which is 3 by 2. The right hand side should be 7.
Yes, which is this dimension 3 by 2, but it can convert a field from dimension 3 half. So this is still dimension 3 half, because epsilon is dimension minus half. This has to be the same dimension. That's the reason. There's an epsilon sitting here. So this is, F is a field of mass dimensions 2. Now we have given this transformation properties of phi, transformation properties of psi. These transformation properties have to have this property, because that's what the algebra is. Which means now if I evaluate delta 1, delta epsilon 1, delta epsilon 2 commutator on phi of x, I should be able to evaluate that, because I know how this transforms. First transformation, second transformation on psi I have prescribed. So I should be able to calculate this. Two transformations of phi with parameter epsilon 1 and epsilon 2, and do the reverse order and take the difference. That's what this is. I should be able to compute this, and I should get on the right hand side this. Is that clear? And if you do that, that fixes this coefficient the way we have written it. F disappears. So minus twice epsilon 1 sigma mu epsilon 2 bar minus epsilon 2 sigma mu epsilon 1 bar times d mu phi of x, and I here.
Why you added this fx?
There is some freedom in doing that, so let me put it in.
No, but then you will have difficulty in writing a renormalizable.
Well, we'll come back to that question.
Already in my dimension.
Yes, so we'll come to that question. Good question. Not renormalizable, dynamics also. Yeah. Yes? F will also have the transform that I must, in order to complete that, I must provide the transformation of F also. So far I have introduced 3 fields in my multiplet, phi, psi and F. I have given the transformation rule for phi, transformation rule for psi. Now I have to provide transformation rule for F. So this fixes the coefficient in front of d mu phi for delta psi. Now I have fixed this, and with that I have realized that on phi the supersymmetry algebra is realized. Now I must do the same on psi. So why did I write psi? Yes. So let me do delta epsilon on psi alpha. Do two supersymmetry transformations, one with parameter epsilon, one with parameter. This will convert this into, so let me say, write it, and psi is root 2 I sigma mu epsilon 2 bar alpha d mu phi plus root 2 epsilon 2 f of x. That is the first transformation on psi. Then let me do the second one. The second one will act on this. That's what it is. Now we will reorganize this term. There is something called Pairs identities. One particular of them, we'll have a little more discussion of Pairs identities later. Let me use it here and then I'll show you how to get that. Take a fermion lambda bar alpha and multiply it by phi psi. Phi is a fermion in this notation. Please don't confuse it because I need so many symbols now. So phi is a fermion here. So three fermions. You can rewrite this product as minus half sigma bar nu psi alpha dot phi sigma nu lambda bar for three fermions lambda bar phi and psi. This identity is true. Lambda bar is another fermion in zero half representation. This bar has nothing to do with the bars we write in a four component notation. Okay. Now look at this term carefully. Let me write it here. It is sigma mu epsilon 2 bar alpha. Sigma mu alpha, alpha dot. So free index is alpha, so I just write it like this. Times d mu epsilon 1 psi. Epsilon 1 is a constant object, I can take it out in d mu. Now call this lambda bar. Just rename it to go to that. Call this object phi and call d mu psi. So let me put this epsilon 1 d mu phi, d mu psi. Call this phi and this together call it psi. Just renaming and use that identity for this portion. So this is sigma mu outside and then minus half sigma bar nu, and psi is d mu psi, and phi is epsilon 1 sigma nu epsilon 2 bar. In order to use this identity, rename this as lambda bar, rename this as phi, and rename this d mu psi as psi, and use that identity to rewrite this. D mu psi is lambda bar, epsilon is phi, epsilon 2 bar is lambda bar. That's what this was. No, something is not right. D mu, this whole thing is psi. It's just using this identity to rewrite this. Next, use sigma mu bar is minus sigma mu bar plus twice eta mu nu. That's the algebra of sigmas. So the eta gives you here, this contracts with this, 2 goes away, and there is a minus d epsilon 1 sigma nu epsilon 2 bar d mu psi. Do I have the sign right? Yes. That is this term with the eta. And then second term is plus half sigma mu bar d mu psi epsilon sigma nu epsilon 2 bar. Now substitute this here. And then do the same thing with epsilon 1 and epsilon 2 interchange and subtract. So what do you get? Delta epsilon 1 delta epsilon 2 minus delta epsilon 2 delta epsilon 1 . Or let me put a commutator here, so no long rand. Commutator of this acting on psi alpha. root 2 will give you a factor of 2, and there is an I here and there is a minus sign here. So minus 2I epsilon 1 sigma. This is same as this, right? Because this was eta mu. Sigma nu epsilon 2 bar, and interchange will give me epsilon 2 sigma nu epsilon 1 bar times d mu psi. That's the first term. Now from the second term, you will get this half will go away with root 2, and root 2 is 2 here. There is an I there. I sigma nu sigma mu bar d mu psi alpha epsilon 1 sigma nu epsilon 2 bar minus epsilon 2 sigma nu epsilon 1 bar. Plus root 2, the F terms, epsilon 2 alpha delta epsilon 1 of F x minus epsilon 1 alpha delta epsilon 2 of F x. This is nice piece because this is what we want, because that in order that algebra is realized on fermions, this is the part we want. This is the extra part. This must cancel, which tells us how to fix the transformation properties of F so that it cancels. And in fact, I think this term and this term will cancel. Last terms cancel if delta epsilon of Fx is written in this form: I root 2 epsilon bar sigma mu bar d mu psi. Or you can write it equivalently as interchange d mu psi sigma mu epsilon bar. You can interchange this and this, convert sigmas into unbarred and change the sign. And that is for any fermion chi sigma bar mu lambda bar is same as chi bar lambda is same as minus lambda sigma mu chi bar. So if you give this transformation rule for Fx, then those two terms cancel. But in order to see that cancel, you have to do a phase rearrangement again. Now, what is the phase rearrangement you have to do? There's another identity. Use the identity for 3 fermions phi lambda bar chi bar, phi alpha lambda bar chi bar. This is contracted, alpha dot down, alpha dot up, same as minus half sigma nu chi alpha lambda bar sigma nu phi, or same as plus half sigma nu chi bar alpha phi. One of them should have been barred. This is barred, sigma nu lambda bar. Now that's an exercise. Use this identity and show that you can rewrite this times this as this, and this times this. Should I do that, or will you do it? I'll leave it. I'll leave it. So then, now we have fixed the transformation properties of scalars, fermion, and this F field. So that's a complete description of the transformation properties of the multiplet, except that we have not checked one bit. That is that we have checked that on phi this supersymmetry algebra is realized, on psi this is realized, on F is it realized on F? So check if delta epsilon 1 commutator delta epsilon 2 on F is minus twice I epsilon 1 sigma epsilon 2 bar minus epsilon 2 sigma mu epsilon 1 bar. And you realize that this does hold. Just do the exercise with these laws now. Holds. So now we have found a representation of SUSY algebra, the chiral supermultiplet. But before I go on to further discussion, let me spend a little time on these Fairs rearrangements, because these are useful things we use again and again. They are not very difficult. Exercise. Show for 4 spinners chi bar lambda bar phi and psi, chi bar lambda bar phi psi. Chi bar lambda r means it is a contracted object. What it means is this object is chi bar alpha dot lambda bar alpha dot. These together mean phi up alpha, psi alpha down. This is same as minus half chi bar sigma bar nu psi phi sigma nu lambda bar. That's also equal to minus half, interchange these, psi sigma nu chi bar lambda bar sigma nu bar phi. That is same as change the sign and interchange this, chi bar sigma bar nu psi lambda bar sigma nu phi bar. That is also same as psi sigma nu chi bar phi sigma nu lambda bar. This looks a little complicated, but it's a very easy thing to prove. And the tricks to prove it we have already learned. We have mastered them. To show this, first demonstrate that psi alpha chi beta. Take two fermions, psi alpha and chi beta. This is, no, not this one. Take this one. Psi alpha and chi bar alpha dot. And show that this is equal to half chi bar sigma bar mu psi times sigma mu alpha alpha dot. This is shorthand for, let me remind you again, chi alpha or chi bar beta dot sigma mu bar is indexed with a dotted first up and dotted undotted next. This is what it stands for. This is the shorthand for this. And this is not a difficult thing to prove. Why? This is half zero representation. This is zero half representation. So this combination is, this one is half zero representation and this one is zero half representation under Lorentz group. So this product transforms as a vector, half vector under the Lorentz group, right? So therefore I should be able to write psi alpha dot to be a vector A mu times S sigma mu alpha dot. This is what we use in setting up the supersymmetry algebra, the same rule. This is some vector A mu sigma mu alpha dot. Multiply this by bar nu alpha dot alpha. Sigma bar nu alpha dot alpha. What do you get here? You get sigma nu bar psi alpha dot bar alpha dot alpha, and here you get A mu sigma nu alpha dot sigma bar, this is mu alpha dot alpha. What is this object? And what is this object? This is trace of sigma nu bar is now look at this object. I take chi bar across to this side, chi bar dot this side. But since I take it across side, I have to change sign. So this I can write as chi bar dot minus sigma nu bar alpha dot alpha psi alpha. Take chi bar across psi, and this is just number matrix element, so I can take it around sigma with a change of sign and rewrite this as this. But this object is nothing but minus chi bar sigma. So that tells you here A nu is minus half chi bar sigma bar nu something new up down has gone. Oh, so maybe I should have put new up here. So this is new up here. So this is new up here. This is new up here. Is that? And that's the identity. No more than this rule gives you this identity. Now I leave two exercises which I won't do in detail for you to check. Yes, before I say that, now look at this 4 fermion identity. This 4 fermion identity is the same identity as this one, except that you contract it with 1 lambda and phi, both sides. This identity is the same as that one. Similarly, show that psi alpha chi beta is equal to 1/2 delta alpha beta psi chi minus 1/8 psi sigma mu nu chi sigma mu nu alpha beta, and psi bar alpha dot chi bar beta dot is 1/2 delta alpha beta psi bar minus half psi bar sigma mu nu chi bar sigma, 1 up and 1 down. Hint. This one, for example, this one is a product of half 0 and half 0, the first one, and half 0 is a singlet plus 1 0. So this would be made up of a singlet and 1 0. 1 0 is the self-dual representation, spin 1 self-dual representation of Lorentz group. Half 0 0 is, 0 is spin 0 is this. This object is self-dual because sigma mu nu's are self-dual. So this object is that. So what does that tell us? What you do is that you write this as where B mu nu is self-dual. This is the most general thing you can write. Then solve for A and B coefficients by multiplying by sigma mu nu, or just simply take the trace of sigma nu is 0. Trace of alpha beta is 2. So that tells you A twice A is psi times chi contracted. And that's what it is, half of this. That gives you the first term. Second, multiply by sigma mu nu, both sides. And this will take the trace of that will be 0, that will give you B mu, and B mu will work out to be exactly this. Okay? And for the second one, we have the rule the product of 0 half and 0 half representation is 0 0 0 1. This is anti-self-dual representation. So which means you write psi alpha dot chi dot beta dot to be A bar times delta alpha dot beta dot plus B mu bar sigma bar mu nu alpha dot B dot. This is anti-self-dual. And obtain the next one. Is that clear? There's another identity which we can look at. This one. You put indices on them and take fermions out. Peel them off. You will get an identity, another identity, which is useful to remember. Delta alpha beta, delta alpha dot, del alpha dot beta dot delta alpha beta is 1/2 sigma nu alpha dot beta sigma nu down alpha beta dot. It's this identity with fermion's field law. So anyway, that completes our discussion on Ayer's rearrangements. Play with them for a while and you'll get used to it. Let's go back to now the representations of SUSY. So what did we find? We found a chiral representation or chiral supermultiplet, also called Wess-Zumino supermultiplet, because those were the guys who obtained this representation first. Made up of a complex scalar and a fermion and another scalar fx. With the transformational rules, let me summarize that. The various components of this supermultiplet, the three components, two bosonic, one fermionic, have mass dimensions of phi, psi, and f are 1, 3 and 2. That's one observation. We know what mass dimension 1 field, scalar field is. We can write a dynamical field theory for that. We know how to write spin 3/2 objects, dynamical field theory. But mass dimension 2 objects, we cannot write a dynamical field theory for. So F cannot be a dynamical field. F cannot be a dynamical, or otherwise we'll also use physical field. So there's a name we give to this field, auxiliary field. Which means we will not write a kinetic energy for F in our theory. But they could have equations of motion, but the equations of motions will not be dynamical equations of motion. So they will be governed by constraints equations. F will be governed by constraint equations. Dynamical equations means equations which have second time derivatives. So we will not prescribe them as having some evolution with by an equation with two derivatives of time. They will only be prescribed by equations which don't contain two derivatives of time. So those equations we call constrained equations. So that's one observation. Second observation, in this multiplet, we have two real bosonic fields, because a complex field is made up of two real bosonic fields, phi of x, and two real bosonic fields in fx, because f is also a complex field. So four real, total four real bosonic fields. Psi x is made up of two complex fields for psi 1 and alpha 1 and 2. That is four real fields. Four real fermionic fields. So there is Bose-Fermi equality of degrees of freedom.
How do you conclude that f is fully at two real bosonic?
It's a complex field from the construction.
Only dimensions between what is.
No, it's dimension 2, it's a scalar, it's a Lorentz scalar, and a complex field. Right? Now, in this count, we have counted f degrees of freedom of f also, which means we have not used the constraint equations to tell you that f is not an independent field. We have counted f as an independent field. We have also not used the dynamics that phi and psi have. So this is off-shell degrees of freedom. Degrees of freedom, off-shell. Which means phi, psi, and f don't satisfy equations of motion. They're general fields. Now, on-shell degrees of freedom. On-shell degrees means phi and psi and f satisfy equations. But we said f cannot have dynamical degrees of freedom. It cannot have dynamics. So it's not an independent degree of freedom. So f is not to be counted. F would be a constraint, which means f would be a function of other scalar, other fields. For example, it would be a function of phi's. So the only degrees of freedom you have to count in f, in phi and psi. So on-shell degrees of freedom of a scalar, complex scalar field are two real in one complex field phi x. And how many on-shell degrees of freedom do I have in a fermion, left-handed fermion? How many, let's start with Dirac fermion, people understand better. How many degrees of freedom do I have a Dirac fermion? Dirac fermion is made up of 4 complex objects. But when I use equations of motion, how many degrees of freedom are there? 2 particles, 2 antiparticles. 2 particles spin up, spin down, antiparticles spin up, spin down. There are only 4 degrees of freedom. Dirac fermion is made up of 4 complex objects, but it has only 4 real dynamical degrees of freedom, not 8. The reason is because it satisfies Dirac equation. Dirac equation takes away half the degrees of freedom. Okay. Now same about left-handed fermion. That's half the count. It's made up of 2 complex objects, but equations of motion, Dirac equations of motion, or Pauli equations of motion for left-handed fermions. Take away 2 of them, you are left with only 2 degrees of freedom. This is how we counted when we did the representation on one particle states, because there we counted physical degrees of freedom. For a left-handed fermion, we counted only 2 degrees of freedom. For massless fermion, we said there are only plus half and minus half 2 helicities. Okay. So 2 real and 2 real in psi alpha. So again, on shell equality of Bose Fermi degrees of freedom. This will always be true. On shell degrees of Bose. But we'll get examples of where this may not be true. Off shell may not be true. And we'll see in what context it can happen. So this was, I'll take 5 more minutes and close this discussion. So this was a chiral supermultiplet. Chiral supermultiplet, this was the left chiral supermultiplet, where we said that this multiplet does not transform under the right-handed supersymmetries, which means Q bars. Now I could do the other way around. Take an anti-chiral multiplet. Anti-chiral multiplet would be one with epsilon Q acting on, let me give it a name, phi star. Here. The Q supercharges don't act on this multiplet. Q bars act on it. And the same argument I can go through and construct the multiplet phi star x and call it. Then the fermionic component of this multiplet would be in 0-half representation, in the right-handed representation. So this is in 0-half representation, chi x, and some f star, call it the auxiliary field. And transmission properties I can read it off, do the whole exercise, or I can read it off here. What would it be? It will just be conjugate of what I have there. So root 2 epsilon bar chi bar root 2 I sigma mu epsilon bar alpha dot So is that right? That's what it would be. The antichiral multiplet. Where? Chi is minus, this one is with plus, and then this should be with minus. Is that what I have here? Yes. All these remarks are valid for that one also. But there's one last observation, and an important observation. SUSY transformation of F or F star, which means F from the chiral multiplet or F star from the antichiral multiplet, is a total derivative. Epsilon is space-time independent. So I can just rewrite this as this is a total derivative. So is the F star transformation. This is an important property. Auxiliary fields transform by total derivatives. Okay, we stop at this.